Of course. Of course MIT would throw something like this. For those who don't know, that pi product is like that's from a math contest or like from a math Olympiad problem. In fact, this might be even a Putnam product actually. This pi product, I think this could be from Putnam actually. Now I think about it. I don't know if it's exactly from Putnam. Probably not, maybe. It looks like it. This does look like something in a Putnam exam, like back in the old days. Maybe. I don't know. But this is definitely a Math Olympiad problem where you have to evaluate this. And of course, they threw it in an integral. So to any competitors who had this and they were going against a Math Olympiad, I'm so sorry for you. But you are kind of done for if you don't know how to solve this. But in general, if I was a Math Olympiad, I would definitely obliterate you saying, oh, I know this problem. I've seen this problem so many times. This is equal to sine x, and then times x here. This is negative cosine of x, and then 0 pi over 4. Oh, would you look at this? Pi minus 1. This is, oh no, this is plus 1. 1 over 2. Oh, here you go. Done. And then they just beat you in like 30 seconds. And then it's like, it's no fair because you've never seen this problem before. So, stop throwing Math Olympiad problems in an integral. Okay, now, how on earth would you actually solve this? So, what is going on in this pi product here? So, to take a look, right, let's deconstruct this, right? If you ever, for any sum or product, you know, if there's a sum that you have to solve for and it looks very awkward and weird, deconstruct it so that we know what is going on. Okay, so we have cosine of what? Plug in 1, let k equal to 1. We get cosine of x over 2. Okay, and then we have times cosine of x over 4. Then cosine of x over 8. Cosine of x over 16. And then cosine, then it goes on. And then all the way up to some cosine of 2 to the power of whatever n. Okay? So here, we don't know where this is going to lead to. However, notice what happens if I just kind of, you know, multiply this by what? Sine of x 2n? Right? What happens then? Oh, and let's actually multiply this by 2. Right? Then what you're gonna get here is you end up getting 2. I'm sorry, not 2. You have 2 times this and this. We get sine of x over 2 times, pretty much 2x over 2n, which is 2n minus 1. Okay, and then you do it, and then what you just did is you caused a chain reaction. So, for example, like if because I know this portion here is a little distracting. Okay, because that's like all variable stuff. But let's say, for example, here, right? We stopped at here. What happens if I just, oh, let's be one of those whatchamacallit, those juvenile teenagers who likes to destruct things. What happens if I just light this on fire? And so you cause a chain reaction, right? And then here you just, okay, let's do times 2 on both here. Now this is now sine of x over 8. Oh, let's multiply 2 again. And now this here is like sine x to the power of, x over 4. Oh, let's multiply by 2 again. And now this is all sine 2x, sine of x over 2. And then you do it again. And then you end up getting like sine of x over 2 to the power of 4 sine of x over 2 to the power of 4. Ah! Now, do you see a pattern here? right? Just by this example, we know a generalization immediately, right? We know that now if we apply the same thing, oops, I did not like that. If we apply the same thing for n numbers, right? If we apply the same thing for cosine x over 2, cosine of x over 4, all the way to cosine x to the 2n power, okay? Notice that we can do the same thing here. So now this with this is equal to sine of x over 2 to the power of n of sine of x over 2 to the power of n. Okay? And now you're probably thinking, okay, but Silver, why are we using n? This should be infinity. Well, let me tell you. Okay? Yes, this is infinity. Okay? But I'm just generalizing it, right? If this was n, then this is what the pi product would equal. Okay? Now that we have infinity, now this pi product, this infinite pi product, is now equal to the limit as n approaches to infinity of sine of x 2n sine of x over 2n. Okay, now what is this? I think it was just easier if I just rewrite it, because this is a constant, technically, in this limit. Okay. X 2 to the power of n, and this is 1 over 2 to the power of n. In order for this to converge, I need this to have an x. So I need an x here, but because I borrow an x, I need to do 1 divided by x. Okay, this is now equal to sine of x over x, and this limit here is equal to 1. And I know some of you guys are thinking, wait, that does not look right. Well, if I do a u substitution, right, let u equal 1 over 2n, then what happens is n as n approaches to infinity, what do you get? U now approaches to 0. And so now what you have is you have xu over sine of xu. Does that look familiar? Right, you should know this. You should know this limit. This is equal to 1. This whole thing is now sine of x over x. But for those who don't know, right, the limit as n approaches to 0, sine of n over n, this is equal to 1. Okay? And we use this a lot as a baby limit when we solve for complicated stuff, more complicated limits. So, for example, like sine of n over n, how do we properly solve this? Well, what we do is we let sine of n, and we need sine of n at the bottom, and then sine of n on top, and then n here. Oh, this is equal to 1, and this is equal to 1. This whole limit equals to 1. Okay, so we're using this as our baby limit. Now, you can also reciprocate it. So if this is equal to 1, then the limit as n approaches to 0, n over sine of n also equals to 1. And then whatever the function this is, okay, whatever the function this is, times n, you have this times f of x n is also equal to 1, because f of x is treated as a constant. Okay, so that is why this and this whole thing is equal to 1. I would like to argue, like, if you have a limit of some whatever a, and this L equals to 0, then obviously the limit of whatever function is going to equal to infinity. So technically it does work, but in real analysis they consider it as an illegal move. So this is, but going again with this integral, we now know that this is equal to, from 0 to pi over 4, x times sine over x, sine of x over x. This is equal to sine over x, sine of x. I don't know why I'm saying sine over x, but this is sine of x. And so now you can easily compute this. This is equal to, you guessed it, this is now simply 1 minus 1 over root 2. Okay, and that is our answer. Alright, so that's how you solve this pi product. It's, you generalize it, you take the limit, using a baby limit that we already know, and then it equals to sine of x over x. Okay? Alright, I hope that helps, and I'll see you guys in the next video.